Hello dear students, welcome back to our YouTube channel. As you know that we are studying about integral transform, in which we have started our second chapter, Laplace transform, in which we have seen the definition of Laplace transform as Laplace transform of f of t, Laplace transform of f of t is equals to integration from 0 to infinity e raised to minus st f of t dt. And the main purpose of using Laplace transform is to convert differential equation into algebraic form. Why? Because we want to solve that differential equation by using algebraic form, and we want to solve differential equation by easy method using algebraic form. So we convert that function or ordinary differential equation into algebraic form to get solution in an easy method. Now after seeing definition of Laplace transform, we have seen Laplace transform of some basic functions such as 1, t raised to n, e raised to at, sin at, cos at, and many more. After that we have learned some theorems which are depend upon Laplace transform, in which we have seen the linearity property, then first shifting property, then change of scale property, Laplace transform of differentiation, Laplace transform of integration, Laplace transform of function having multiplied with t raised to n, Laplace transform of function which is divided by t. Such type of theorems we have already seen, and we have seen some basic examples which are based upon linearity property and shifting property. Now we will see some advanced example, in which the first example is as follows. Find the Laplace transform. Find the Laplace transform and prove integration from 0 to infinity sin t by t is equals to sin t by t dt is equals to pi by t. Correct? Here we have integration from 0 to infinity sin t by t dt. We have to prove it becomes pi by 2. Since we have sin t by t, means we have function which is divisible by t. So first of all, the function f of t is given as, let f of t is equals to sin t, and since we know Laplace transform of sin at is equals to a upon s square plus a square. Correct? We have already done this basic Laplace transform of basic function, in which we have seen Laplace transform of sin at is equals to a upon s square plus a square. Since we have sin t here, a is equals to 1, so we have Laplace transform of sin t only is equals to 1 upon s square plus a square. Correct? We have Laplace transform of sin t is equals to 1 upon s square plus a square, and we have the function to find Laplace transform sin t upon t, which will give us, since we know that Laplace transform of f of t upon t is equals to integration from s to infinity f of u t. Correct? We have the Laplace transform of sin f of t upon t dt is equals to or we can say that Laplace transform of integral function which will give us integration from s to infinity f of u du. That's why if we take Laplace transform of, why we have calculated Laplace transform of sin a t? Because we want capital F of u, which means f of u means Laplace transform of f of t. That's why we have calculated the Laplace transform of sin t. Now, since Laplace transform of sin t upon t will give us integration from s to infinity f of u, means replace s by u and we will get 1 upon s square plus 1 square. Sorry, here we have a is equal to 1, so we can write it as s square plus 1 square, and that is 1 du. Replace s by u. Now we have to calculate integration from s to infinity 1 upon u square plus 1, and we know that we will get tan inverse of u as to infinity. Correct? And after putting the limits, we will get tan inverse of infinity minus tan inverse of s. And tan inverse of infinity will give us pi by 2 minus tan inverse of s. And if we replace, and if we see pi by 2 minus tan inverse of s, we will get cot inverse of s, and it is equal to tan inverse of 1 upon s. Correct? So Laplace transform of sin a t upon t is equal to tan inverse of 1 upon s. So we will get integration from 0 to infinity. Here we have integration s to infinity 1 upon u square plus 1 will redo is equal to 1 upon s. Correct? But we want integration from 0 to infinity, so putting s is equal to 0, so we will get tan inverse of 1 upon s, which is equal to pi by 2, and we get integration from 0 to infinity. The function sin t upon t is equal to pi by 2. And it is the required result of our question. So in this example, we have the question: find the Laplace transform and prove integration from 0 to infinity sin t upon t dt is equal to pi by 2. Since we have sin t upon t form, means we have to use the theorem in which we have function which is divisible by t. So using that theorem, we can solve this question. But before going to solve, we know Laplace transform of f of t upon t is equal to integration from s to infinity f of u du, and f of u represents Laplace transform of f of t. So first of all, we have to calculate Laplace transform of sin t, means numerator, and Laplace transform of sin t is 1 upon s square plus 1 square, and Laplace transform of f of t upon t means Laplace transform of sin t upon t is equal to integration from s to infinity, replace the sin of t by Laplace transform of sin t, and it becomes 1 upon u square plus 1 du. And after integrating this, we will get tan inverse of u, and limits are from s to infinity. By putting this limit, tan inverse of infinity minus tan inverse of s, tan inverse of infinity is equals to pi by 2 minus tan inverse of s as it is tan inverse of s, and pi by 2 minus tan inverse of s becomes cot inverse of s. And if we want to convert this cot inverse of s into tan inverse, we will get tan inverse of 1 upon s. Since we have integration from 0 to infinity, so we will get integration from 0 to infinity by choosing s is equals to 0. By choosing s is equals to 0, the integration becomes 0 to infinity. 1 plus u square plus 1 du is equals to tan inverse of 1 upon 0. And 1 upon 0 becomes 1 upon 0 becomes infinity, and tan inverse of infinity becomes pi by 2. Correct? And 1 upon u square plus 1 is what? Is sin t upon t. Correct? So we will get integration from 0 to infinity sin t upon t is equals to pi by 2. Correct? Now we will see one more example. An example is as follows. Find Laplace transform of sine hyperbolic t. Since we know that Laplace transform of f of t upon t is equals to integration from s to infinity f of u du, where f of u is Laplace transform of f of t. Correct? So Laplace transform of f of t means sine hyperbolic t will gives us 1 upon s square minus 1 square is 1, and Laplace transform of f of t upon t becomes integration from s to infinity 1 upon u square minus 1 du. Correct? We have u square upon, now we can write this as integration from s to infinity 1 upon u minus 1 and 1 upon u plus 1. Correct? du. And if which can be written as 1 upon 2 of integration s to infinity 1 upon u minus 1 minus 1 upon u plus 1 d. Correct? And 1 upon 2 is equals to integration s to infinity 1 upon u minus 1 du minus s to infinity 1 upon u plus 1 d. We will get 1 upon 2 log of u minus 1 s to infinity and log of u plus 1 s to infinity. Correct? So we can write it as 1 upon upon 2 log of u minus 1 u plus 1 as to infinity. Correct? And after putting the values of s and infinity at the place of, or we can write it as 1 upon 2 log infinity upon infinity, or u upon u, 1 minus 1 upon u, and 1 plus 1 upon u. So we write it as to infinity 1 by 2 log of 1 minus 0, 1 plus 0, and minus log of 1 minus 1 upon s and 1 plus 1 upon s. Correct? So we will get 1 upon 2 log of 1 is equal to 0 minus log of s minus 1 upon s plus 1, and which is equal to minus log of under root s minus 1 s plus 1, and it is the required result for Laplace transform of sine hyperbolic t upon t. In next lecture we will see some more examples based on integration and differentiation of Laplace transform. Till then, thank you. Bye.